Hello student, in our previous video we started our third chapter, that is the photovoltaic systems, and we have covered the introductory part of the photovoltaic system. And in this video we start with the second point of our chapter, that is the photovoltaic principle. That means the basic working of the working of the solar cell, which is based on the photovoltaic principles. Photovoltaic principle means photo means light and voltaic means generation of the voltage. That means with the help of light we are able to generate the voltage, and this is known as the photovoltaic principle. Two important steps are involved in the photovoltaic principles. These are, that means there are two steps which are involved in the photovoltaic principle or photovoltaic process. So first is the creation of pairs of positive and negative charges called electron hole pair in the solar cell by absorbed solar radiation. That means the first step is the solar radiation. The solar cell is placed in the sunlight so that it can absorb the solar radiation, and after the absorption of the solar radiation there is a creation of positive and negative charges, and it is also called as the electron hole pairs. So there is a generation of the electron hole pairs due to solar energy absorption. So this is the first step, and which is very important step, initial step. Second step is the separation of positive and negative charges by potential gradient within the cell. That means after creation of the or generation of the electron hole pair, there is a separation of the positive and negative charges. That is there is a, at the one side electrons are collected and the other side at the holes which are present, and due to the separation of the negative and positive charges there is a potential gradient. That means there is a generation of the electricity or electric field within a cell. So these are the two main important steps in the photovoltaic principle. So let's see. For the first step to occur, the cell must be made up of a material which can absorb the energy associated with the photons of sunlight. That means the first step, for the first step, the important parameter is the solar cell is constructed with the help of the material which are able to absorb the solar radiation, and after after absorption of the solar radiation there is a creation of the electron and hole pairs. So this material is play very important role. So this material is like that, so that it can absorb the maximum solar radiation and creates the maximum electron hole pair generation. So we are able to obtain the electricity from that. So the energy of a photon E is related to the wavelength by the equation. We know that the relation between the energy wavelength and velocity of light. So this equation is given by E is equal to Sc by lambda. That means simply we know that the single photon which has a energy, that is in a quantum mechanics, it is a photon which has a energy. Photon is a quantum particle and which has a energy E is equal to h nu, but where E is the energy of photon, h is the Planck constant, and nu is the frequency of that. And also we know that c is equal to nu lambda, that is the relationship between the velocity of light, frequency and wavelength. So after substituting the value of nu, that is the nu is equal to c by lambda, we are able to obtain the equation, that is E is equal to Sc by lambda, where h is the Planck constant and the value of Planck constant is the 6.62 into 10 to the power minus 34 joule second. This is the value of Planck constant, and which is the standard value in a quantum mechanics. Next, c is the velocity of light, and we know that the velocity of light is the 3 into 10 to the power 8 meter per second. So this is the equation for the energy of photon. But why we consider the energy of photon? Because the solar light consists of different photons, and the energy of the single photon is E is equal to h nu, and the value of E can be calculated with the help of three different values, that is h, c and lambda. If we know the wavelength of the solar radiation, we have the constant, that is the h and c, then we are able to calculate the energy of photon. The material for absorbing the energy of photons of sunlight are the semiconductor materials. That means for the absorption of the sunlight, generally we use the semiconductor material. That is, these materials are used to construct the solar cell. We know that the semiconductor, what do you mean by the semiconductor? There are different types, that is metal, insulator and semiconductor. But in a semiconductor, again there are two types, that is the intrinsic semiconductor and extrinsic semiconductor. The intrinsic semiconductor is the pure form of the semiconductor. That means the original pure form of the semiconductor without any doping or impurity. And the second type is the extrinsic semiconductor, that is the semiconductor which is doped with the help of other impurities. That is trivalent impurity, pentavalent impurity, and depending on that impurity addition, that is the impurity which is added to the pure semiconductor, there are two types again, that is a p-type semiconductor and the n-type semiconductor. So these are the generally two types of the semiconductor, and these p-type and n-type semiconductor are used in a solar cell for the construction of the solar cell. So first we see what do you mean by p-type semiconductor and n-type semiconductor. So let's see, first is the p-type semiconductor. The p-type semiconductor can be defined as once the trivalent impurity atom such as indium, gallium are added to an intrinsic semiconductor, and then it is known as a p-type semiconductor. Generally, the p-type semiconductor is the semiconductor which is made with the help of trivalent impurity atoms such as indium, gallium, boron. These are all the trivalent impurity atom. Trivalent impurity atom means the electrons which are present in their valence shell is the 3. That is the 3 electrons which are present in their valence shell or outermost shell. So this impurity atom, this is the impurity atom, that is the trivalent impurity atom which is added to the intrinsic semiconductor, that is the original semiconductor, and after that there is a formation of the p-type semiconductor. So this is known as the p-type semiconductor. In this semiconductor, the majority charge carriers are holes, whereas the minority charge carrier are the electrons. That means the p-type semiconductor. In the p-type semiconductor, there is a doping of trivalent impurity in the original semiconductor. And trivalent impurity means it consists of 3 electrons in their outermost shell, and there is a formation of bonding between these electrons, and generally which is the covalent bonding. And in a p-type semiconductor, due to addition of trivalent impurity, there is a lots of holes as compared to electrons. So the minority charge carriers are the electron and majority charge carriers are the holes. The holes density is higher than the electrons density. As we seen, the number of electrons which are present in the p-type semiconductor is less as compared to holes, and the maximum concentration of the holes, so the density of the holes is large as compared to the density of electrons. The acceptance level mainly lies near to the valence band. In the semiconductor, we know that there are two types of band, that is the valence band and the conduction band. Valence band which is at the bottom and the conduction band which is at the upper, and the energy difference between these two bands is the generally band gap of that semiconductor. Band gap means the energy difference between the valence band and the conduction band, so that if we incident a photon of energy which is equal to the band gap of that semiconductor, so that the electron gets excited from valence band to conduction band after the absorption of the photon. So the acceptance levels mainly near to the valence band. But why this? Because in a p-type semiconductor, the concentration of holes is more, and at the valence band, so the acceptance levels is present at the valence band. The second type is the, before going to start second type, the example of the p-type semiconductor is the, that is a silicon is a pure semiconductor, and there is a addition of trivalent impurity, that is a trivalent impurity atom is a gallium arsenide or boron atom, and trivalent impurity means the outermost shell of that atom is consist of 3 electrons, as as shown in the figure, boron has a 3 valence electron and which are bonded to the silicon electron. So with the help of covalent bond, that is a formation of covalent bond between the silicon electrons and the boron electrons. So the bonding takes place with the help of that, and there is a void space. That means the valency of the boron is the 3 in this case, but the silicon consists of 4 electrons in their outermost shell, but the 1 electron is remains as it is. So the valence electron of the boron atom does not able to form the bond with the silicon. So this is all about the holes, the formation of the hole due to deficiency of the electrons. So the number of holes in the p-type semiconductor is large as compared to n-type semiconductor. In this way, the large number of holes are present in the p-type semiconductor. Now the second type is the n-type semiconductor. The n-type semiconductor can be defined as 1. The pentavalent impurity atoms such as antimony, arsenic is added to an intrinsic semiconductor, and then it is known as the n-type semiconductor. As we seen, when n-type semiconductor is formed, that is, as we seen how the p-type semiconductor is formed. Similarly, the n-type semiconductor is formed, but the difference is that there is a pentavalent impurity. That means there is addition of pentavalent impurity to the intrinsic semiconductor. So the pentavalent impurity means there are 5 valence electrons which are present in that atoms such as antimony or arsenic. So this is all about the n-type semiconductor. In this semiconductor, the majority charge carriers are electrons, whereas the minority charge carriers are holes, as we seen in p-type semiconductor. In a p-type semiconductor, the majority charge carriers are the holes and the minority charge carriers are electrons, but in n-type semiconductor, the majority charge carriers are the electrons and the minority charge carriers are the holes. The electron density is higher than the density of holes. That means the electron density is large as compared to density of holes in the n-type semiconductor. That is opposite to the p-type semiconductor. The donor level mainly lies near to the conduction band. That is the number of electrons which are present in the n-type semiconductor is large, so the donor level which is lies near the conduction band. This is the n-type semiconductor. That means the silicon is doped with the pentavalent impurity, and pentavalent impurity atom which is the antimony, and antimony consists of 5 valence electrons. So these 5 valence electrons form bonds with the silicon atom, and these 4 electrons forms bond with the 4 different atoms. So this is all about that, and the 1 extra electrons is remains, and which is free in that semiconductor. So this is the n-type semiconductor. That is there is the excess of electrons which are present in the semiconductor. That is the concentration or density of the electrons is more as compared to holes. So this is the n-type semiconductor. The material suitable for absorbing the energy of the photons are semiconductor like silicon, cadmium, telluride, gallium arsenide. As we seen, the semiconductor material plays very important role in the solar cell. So different types of the materials which are used for the absorbing purposes, that is the silicon, cadmium, telluride, gallium arsenide. These all are the semiconductor materials. In a semiconductor, the electrons occupy one of 2 energy bands, and the valence band and the conduction band. That means the electron occupy one of the 2 energy bands. That means there are 2 bands, that is the valence band and the conduction band. The electrons may present in the valence band or conduction band. So this is that the valence band has electrons at a lower energy level is fully occupied, while the conduction band has electrons at higher energy levels is not fully occupied. That means if we consider the condition of the semiconductor at normal temperature, there is a conduction band and the valence band. The energy level corresponding to valence band and the conduction band has electrons, but the energy level for the valence band is at the low level, that is and which is fully occupied at normal temperature, and for the conduction band the energy level higher, which is at the higher energy level, and which is not fully occupied. When we incident the photon, then there is excitation of the electron from valence band to conduction band, and after that we are able to obtain the electrons which are present in the conduction band. So this is all about that. The difference between the minimum energy of electrons in the conduction band and the maximum energy of electrons in the valence band is called as the band gap energy. That means the valence band which has a lower energy level and the conduction band has a maximum energy level, and the electrons which are present in the valence band and the conduction band respectively has minimum and the maximum energy. That means the electrons which are present in the valence band which has minimum energy, and the electrons which are present in the conduction band which have maximum energy, and this difference between these two energies, that is maximum energy and minimum energy, is the band gap of that particular semiconductor, and the band gap of different semiconductor is different. The photons of sunlight having energy greater than the band gap energy are absorbed in the solar cell or cell material and excite some of the electrons. That means the sun, if we incident the sunlight on the semiconductor material, and this we know that in the semiconductor material there is a valence band and the conduction band, and generally at a normal temperature the electrons which are present at the valence band, after we incident the solar radiation on that material, the electron absorb that radiation and excite from valence band to conduction band. These electrons jump across the band gap from the valence band to conduction band and leaving behind holes in the valence band. That means after excitation of the electrons from valence band to conduction band, the electron goes to the conduction band, and due to deficiency of electron, we know that due to deficiency of electron there is a creation of holes, that is the positive charge. Thus electron hole pairs are generated. In this way, in a solar cell, the first step is we incident the solar radiation on the semiconductor material. In the semiconductor material there are two types of the band, that is the valence band and the conduction band. At normal temperature the electrons are present in the valence band, and after we incident the solar energy there is absorption of photon. That means the photon which have energy h nu, and which is equal to, if this energy is equal to the band gap of that semiconductor, so that the energy of that photon gets absorbed by that electron and it get excited to the conduction band, and due to excitation of electron in the from valence band to conduction band there is a creation of hole due to deficiency of electrons, and therefore the electron hole pairs are generated. That means within a conduction band there are electrons, and at the valence band there is a holes, that is a positive charge. So in this way the electron hole pairs are created. This is the first step, that is the generation of electron hole pairs in the solar cell or in a photovoltaic system. This is the photovoltaic cell or photovoltaic system or solar cell. It consists of two semiconductor material, that is a p-type and n-type, and we know that as we seen, that is a p-type silicon and n-type silicon. The upper part is the n-type silicon and the lower part is the p-type silicon, which is shown in the figure, and in between them there is a deflection region. That means there is a creation of the electron hole pair and also recombination of the electron hole pair, so that the electricity is generated or voltage is generated. And the upper part, that is the two strips, which is the metallic conducting strip, so which are used for the conduction purposes or to reduce the losses. And the n-type is the generally n-type is the negatively charged and p-type is a positively, and overall the system semiconductor is a neutral, and there is a connection of external load, so that from that the current is a flow, and in this way we are able to obtain the electricity from the solar radiation. As we discuss the first step, that is after incident the solar radiation on the semiconductor material, the semiconductor material absorb that solar radiation or the photons, and if the energy of photons is equal to the band gap of that semiconductor, then there is absorption, so that the electron absorb that photon and it get excite from valence band to conduction band, and due to excitation there is a creation of the hole due to deficiency of electrons in the valence band. In this way electron hole pair generated. And in the second step, after creation of electron hole pairs, there is a separation of electron hole pairs, that is there is a built-in potential, and developing the built-in potential, and due to the built-in potential there is a corresponding electric field. So in this way we are able to obtain the solar electricity from the solar energy. This is the actually principle of the photovoltaic cell. The electrons in the conduction band and the holes in the valence band are mobile. As we seen, the electrons in the present in the conduction band and the holes are present in the valence band, which are mobile. That means they can move freely. They can be made to flow through a external circuit if a potential gradient exists within the cell. Due to separation of the electron and holes, there is a generation of the potential gradient, and due to the generation of the potential gradient or deflection layer or built-in voltage, there are different names for that. So there is a electric field, and due to that electric field there is a flow of current through the external circuit. In a case of silicon, the potential gradient is obtained by making the cell as a sandwich of two types of the silicon, that is a p-type and the n-type. That means in the silicon solar cell, the n-type and p-type material is used, and in between them sandwich of two types of the material, and in between them there is a formation of the p-n junction. As if we consider the case of diode, the same working principle of the solar cell. That means there is a p-type material, n-type material. After the diffusion of the p holes to the n region and electrons to the p region again. This is the vice versa. So this occurs vice versa. So there is a recombination of electron hole pair, and after recombination we are able to obtain the electricity. Then after recombination there is a separation of the electrons and holes, and there is a due to separation there is a voltage. So in this way we are able to obtain the current or electricity, same like in a diode. So the principle is the same. So this is the solar cell construction, that is a p-type and n-type material are sandwiched together so that we are able to form the p-n junction. The n-type material has excess electrons while the p-type has a holes. As we seen, the p-type has a maximum number of holes as compared to n-type, and in n-type the electrons are more as compared to p-type. When these materials are joined together, excess electrons from the n-type diffuse to recombine with the holes in the p-type. That means when we join the two semiconductor, that is a p-type and n-type, as we know the holes are present in the p-type material, which is the majority charge carrier in the p-type, and the majority charge carrier in n-type is the electrons. But these electron and hole, that means the electrons from the n-type diffuse to recombine with the holes in the p-type and vice versa. Similarly, the holes from the p-type diffuse to the n-type. That means there is a opposite process again. As a result, the n-type material becomes positively charged while the p-type is negatively charged. That means after diffusion of electron from the n-type material to the p-type material and vice versa, there is a n-type material. That means from n-type material the electrons diffuse to the p-type material. So there is a neutralization process occur, that is a recombination process. That is n-type material becomes positively charged after accepting the electrons, after accepting the holes from the p-type, and similarly the p-type material is negatively charged, that is after accepting the electrons from the n-type. So this phenomena occurs in the p-n junction, that is a deflection layer. This creates a built-in potential at the junction. That means there is a separation of the electron and holes, and due to this separation there is a potential difference or potential gradient. So this is the built-in potential at the junction. The consequent electric field is adequate to separate the electrons and holes, cause a direct electric current to flow in the external load. If we connect the external load, then all these phenomena, after occurring of all these phenomena, there is a consequent electric field. So this, due to this consequent electric field, to separate the electrons and holes and cause the direct current to the external load. So this is all about the solar cell principle or photovoltaic principle. From that we are able to obtain the electricity from the solar radiation, and the material which is used for that is the semiconductor material. All this happens within the semiconductor material. So the semiconductor material is very important for the solar cell. So this is all about the photovoltaic principle, or how the solar cell works, or how we are able to obtain the electricity from the solar energy. So this is all about that, the photovoltaic principle, and which is very important principle for the solar cell. So next is the different parameters or the IV characteristics of the solar cell, or the different parameters such as the efficiency, fill factor, open circuited voltage, short circuit current. These are all the different parameters which we are able to obtain from the IV characteristics of the solar cell. And as we seen, the solar cell principle is similar as the PN junction diode. So the equivalent circuit is formed with the help of PN junction diode. So this we will discuss in our next video. So we will continue with that.